Every single time. Every time. I need to turn my mic back on. Okay, so looking at mixtures. We have two kinds of mixtures. Okay, this lab is talking about separation of mixtures, so we're talking about mixtures. So, genus, genre, or genus, it means kind. Homo means same, hetero means different. So a homogeneous mixture, it's all the same kind of mixture. Okay, it is uniform throughout. We're talking about a single phase. Could be a single solid phase, like steel. Steel is a heterogeneous solid mixture. Okay? Very often, though, we're talking about liquid mixtures. So, Windex, apple juice, soda. Okay, these are all homogeneous mixtures. They have a single phase. It's uniform throughout. Okay, so every part of the mixture looks like every other part of the mixture, whereas heterogeneous is not uniform. It has two or more phases. Okay, so you can distinguish one part of a heterogeneous mixture from another part. A salad is a heterogeneous mixture. Orange juice with pulp is a heterogeneous mixture. Okay? Chocolate chip ice cream. Okay? These are all things where you can point to one portion of the mixture and say, this is different from that. Okay? So this has uniform physical properties throughout the mixture. This has discontinuous physical properties. One part of the mixture looks different from another, behaves differently from another. So the way you separate mixtures can vary from the very simple to the very complex. Okay? And it depends on your mixtures. It depends on the properties of the things in the mixture. So, I mean, the simplest way of separating mixture is just to physically pick out the bits of the mixture you don't want in there. Like taking the tomatoes out of your salad, because tomatoes are disgusting and gross and wrong, and you don't want them in your salad. I mean, raw tomatoes. Cooked tomatoes are good. Raw tomatoes are bad. Okay. But you can't really do that with salt water. So there are lots of different techniques for separating mixtures that depend on the physical properties of the things being mixed. Okay. So we'll be dealing with, first, different ways of separating things, different ways of purifying things, and we'll be dealing with collection techniques, because it's not enough to separate your things. You need to, collect. You need to keep a hold of the thing you want and get rid of the thing you don't want. So another term that you're going to need, precipitate. Oops. A precipitate is something that comes out of solution. So rain and snow, those are called precipitation because those were water that was dissolved in the air that is falling out of the air. So it's falling out of that solution. SOL''N is my abbreviation for solution. You also need to know about solubility. Okay? If one thing can dissolve in another, it is soluble. And you can say that it has solubility. So solubility is the property of being able to dissolve one substance in another substance. And we measure that in a lot of different ways. Okay, you can measure it, you can do, say, mass percent is a popular form of measuring solubility. So grams of your solute per grams of solution would be a way of measuring your mass percent, because that way the mass of the solute is a percentage, a fraction of the mass of the total solution. Another way you can do, say, grams per liter or grams per milliliter, depends on how soluble it is. If it's very soluble, you can get a lot of mass in a small amount of solution. If it is not very soluble, you might only be able to get a small amount of mass in a large amount of solution. Okay, in that case, you'd be measuring it, how much you've added divided by the total volume of your solution, rather than the mass. Okay. And finally, we also talk about moles per volume. Okay. So there are lots of different ways we can measure the solubility of one thing. It's just how much of A versus how much of either the solution, or it can actually also be you can compare it to just the solvent. How much solvent can you dissolve the solute in? We have a lot of options. Today, we are going to be doing mass percent. The total mass of your solute, just the thing being dissolved, divided by the total mass of your solution. All right. So, different separation techniques. Okay. We got plenty of those. Okay. So, first up, just evaporation. This is a popular one. If you have, let's see. Let's keep you focused. So if you have a solid dissolved in a liquid, if you're confident that there's only the one solid in there, then you know what? You just go ahead, you heat up your solution, and the liquid will be driven off, and you'll be left with your solid residue behind. Perfectly feasible. If you don't live close enough to some salt mine, then you can't mine for salt, but you still need salt to live. Well, if you happen to live near the ocean, then you just collect ocean water, and you either boil off or just wait for it to evaporate on its own. That was, a very popular technique. Still is. Another thing you can do is filtration. Okay, filtration is when you have a solid inside of a liquid, but it's not dissolved. Okay, so filtration, you run, your mixture through some kind of filter. Filter is just basically, it's how to describe it. A filter will let the water pass through, but not the solid. Okay. The filter is itself some sort of solid platform, and it will have holes in it. Okay? It's like a sieve. The size of the holes will determine how much solid can pass through and what solid will be left behind. The solid will be trapped on the surface of the filter. So filters are graded, they're judged by the size of the particles that they block or pass through. We've seen this recently in this pandemic with discussion of things like N95 masks. The quality of your mask is determined by how much, what kind of particles, what size particles, in this case viral particles, it allows to pass through or what it can block. So there's always a trade-off there. A really good filter is going to have those really small pores, and thus it'll trap more solids. But that also means that it's going to be harder for the liquid to pass through, and it'll slow the filter down. So you can do different kinds of filtration. You can just do gravity filtration, where you set up a funnel. You have your filter sitting inside that funnel. You pour your liquid through, and then gravity will, suffice to allow to pull the water through the funnel. But again, that can be slow. So we can also do vacuum filtration, okay, or pressure filtration. Let's see. Okay, so this is a slightly more complex setup. This is a Buchner funnel, okay, or Buchner funnel. Okay. So instead of being, the cone shape that we're used to, this has a flat bottom, and the bottom of this thing has a lot of small holes in it. Once again, though, you set your filter paper on the surface of the funnel, and then if you were doing this in the lab, you would wet the filter paper and you would set it on the filtration or on the suction device. So we use a special bit of glassware. It is an Erlenmeyer flask, as normal, but it has a stem coming off the side. We then attach that stem we run a rubber tube from the stem over to the sink. The sink has a similar stem. Okay? So it's a hollow stem that allows air to pass outside of the funnel. Meanwhile, we have a rubber collar in here so that we get a good seal between the funnel and the glassware. So when you turn the sink on, it takes advantage of Bernoulli's principle. Bernoulli's principle says that Okay. Um, so we get a good seal with this. Okay, Bernoulli's principle. A moving fluid exerts less pressure than a fluid at rest. So when you turn the sink on, you get water streaming past this stem coming out the side, and this creates decreased pressure. So air gets drawn through the funnel along with your solution. The liquid gets trapped down in here, and your solid remains right up there. You could do it in the other direction. We don't have the setup for that, but you can also do higher pressure on this side to push the liquid through rather than using lower pressure on this side to basically pull it through. Same effect. Either way, you have high pressure and low pressure. Okay. So that just speeds up the process. All right. So those are both filtration. If you have a solid and a liquid, obviously this would have to be a heterogeneous mixture, and you can collect the solid on top of here. The reason I said you have to wet the filter paper is because you wet it and then you draw the water through so that you form a good seal against the bottom of the funnel. Otherwise, when you pour your mixture into there, it can flow around underneath and clog up the pores in the funnel. Not only are you not collecting your solid, but you're messing up the funnel. All right. Recrystallization. Okay. So recrystallization is slightly more complicated in that this is something where you have more than one solid dissolved in your liquid. So you can't just evaporate off the liquid. You'd be left with a mixture of solids, and you wouldn't be able to pick them apart. So what you do there is you are dealing with, or you have to take advantage of differing physical properties of the two or more solids that you're looking at. And essentially, solids will precipitate out of your solution at different temperatures, so that you can because they did precipitate out at different temperatures, you can or put it the other way, they'll dissolve at different temperatures. By controlling the temperature, you control the solubility of your solids, and you can separate them out that way. Chromatography. Chromatography, as you'll be using it in this lab, can be used in two different ways. Okay, so chromatography is an older technique, but it has evolved. Okay, if you look at the chunks of the word, the graphemes, chroma or chromato meaning color, graph meaning writing. So the simplest version of chromatography, you have a piece of paper. You put a dot of the thing you're going to be analyzed on that paper, and then you dip the end. You sort of set it in some solution. Okay, the solution will then travel up the paper, based on the it gets wicked up, like being pulled up, like wax being drawn up a wick, and then some or all of the substances that you're analyzed will be drawn up with it because they can dissolve to different degrees in your solution. And then both the solution and the thing you're analyzing will interact with the chromatography paper in different ways, and thus the different things in there will separate. Okay? So it is a separation technique. And so because they're interacting in different ways, they will travel up the paper at different speeds, and the result will be a separation of the stuff that you're analyzing. You can't really see it, but those are different colored dots. All right, called chromato because the things you're looking at have different colors. So one of the ways you can use this is just to analyze the purity of your substance. Do you have multiple things in there? If so, you'll get multiple dots. Another way we can use chromatography, though, is to actually physically separate those substances. if you have a way of getting the dot back off the page, then you could use this. Other forms of chromatography, instead of using paper, they use a tube packed with some material. And then you push the substance that you're looking through it as a liquid or as a gas, and you'll get separation that way. And you can collect the substances at the other end. So you can also use it as a purification technique. When you do this lab, you'll just be doing it as an analysis technique to look at purity. So there's a thing called a retention factor, okay? Because the things are moving at different speeds. The liquid that they're dissolved in will be moving the fastest, and then the different solids will be moving at different rates. So when you're done with your chromatography, your liquid will have moved some distance up the page. Okay, call this, just X. You don't want it to move all the way up to the top, because then you don't know, did the liquid actually stop at the top, or did I, not pay attention and we started getting evaporation off the top, because that would be bad. So you don't do that. So you stop it, before it gets to the top, so that you can actually measure how far the liquid moved. And then your analytes, however many you have, will have moved, different distances up the page. And, you could, if you have a nice pure substance, you'll only have one thing in there. If you have an impure substance, then it will have multiple things in there. Regardless, they will also have moved some distance. So you'll have, A, B, C, etc. And that is the retention factor. Okay, RF is equal to the distance for your analyte divided by the distance that the solution has traveled. And in theory, that retention factor, that percentage, that fraction of the page that it has moved up, would be the same regardless of how far the liquid has moved. Okay, if you had a really long piece of paper, then you would still have moved the same fraction up that really long piece of paper. And that would be a way of identifying your different substances. They would have different retention factors between the substances, but the retention factor would be uniform across different analyses. So you have a mixture where you know that you have substances A, B, and C in there, then you can do a chromatograph of that mixture, and you'll get the 3 different retention factors. And then you could take an unknown, and that unknown would have, just say 2 dots on there. You measure, retention factors for both of those, compare them to the things you measured over here, and you say, oh, this unknown mixture has these 2 things in it. So you can use chromatography in those 2 different ways. We don't have the setup, well, we kind of do, but you're not going to get to play around with the setup, or you could use chromatography to purify. You'll just be using it to analyze. Next up, we have distillation. Distillation is a particularly popular doodad here in the South. We have a long tradition of setting up stills. So distillation is a process that you can use to separate liquids. And it's based upon, the differing boiling points. Okay. So over here you have, your mixture of your 2 liquids, and you heat them up. Okay, it's supposed to be a flame. Heat. Okay, you heat them up. One of them will have a lower boiling point. The other one will have a higher boiling point. So the one with the lower boiling point will come out of the liquid first as a gas. Okay. Then they are going to run through some sort of cooling tube. In the simplest form, this is just going to be a long coil of tubing so that your liquid will be cooled down by the air around it. But you can make it more complicated. You could have basically a nested tube where you have the gas traveling one way and you have cold water traveling the other way to enhance the cooling. The reason you want to do that is first, when you heat up a liquid, you're going to get evaporation even before it boils. This is why, things dry up well below the boiling point of water. And thus you'll have some liquid or some of gas B in here as well as gas A. So the higher boiling point liquid will tend to condense and fall back down into here first. You also, though, want to cool down the other one because you're planning on collecting it at the other end, possibly. Maybe you don't care to collect A, maybe you're just trying to get rid of A, in which case you would just go ahead and let the gaseous A come out the other end and fly away. But maybe you do want to capture it, so after it's run through the cooling, you catch it over here in another tank. So this obviously is a terrible, terrible drawing, but this is, again, like I said, how a still works. You take your crude whiskey over here, you have a lot of water in it, you want a high concentration of your alcohol. So you heat this up. Alcohol has a lower boiling point than water, so it will evaporate first. Then you cool it down, you catch it over here, and you have a much higher concentration of alcohol. So that's distillation. And then you can take this and you can distill it again and get a higher concentration of alcohol. Then again, then again, then again. So you can set up, in fact, this cooling tube acts in many ways as multiplying the distillation effect. And they can get really complicated. They can get really, really interesting. A lot of the really fancy, weird-looking glassware that they use entirely incorrectly in movies is in fact designed for distilling organic chemistry products so that you can separate the thing you want from the thing you don't want. All right, so those are lots and lots of different separation and collection techniques. You wouldn't be doing most of those in lab because it's complicated, it's difficult, it takes time. In the normal course of events, you would be doing just evaporation, recrystallization, filtration, and collecting different products. Okay, so here we're going through just this. You have evaporation techniques. And they're teaching you the safety stuff. That's important. When you actually do get to do in-person lab stuff, you will get to work with some of this equipment. That's why we're doing the in-person lab work, so that you can get the actual hands-on experience with the equipment. This online stuff is more for learning about the theory, about why we do things, a little bit more than how we do them. Okay. So with the Bunsen burner, you would heat up the liquid, drive it off, and you would collect the salt that remains behind. And the way that would work in lab is you would heat up your mixture, drive off all the liquid, and then weigh it. And let it cool down, and then weigh it. You don't want to put the really, really hot evaporation dish directly on the scale. You let it cool down a bit, you weigh it. You heat it again, you weigh it. You heat it again, you weigh it. The reason you're doing this multiple heatings and weighings thing is because you are trying to make sure that you've driven off all of the liquid in there. So you just, as you weigh it, the temperature, the mass will go down, 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 and then it'll stop going down. That tells you that you've collected all of your water, or you've gotten rid of all your water. So that is what you're doing here. Next up, you do filtration. You'll be doing you would be doing a gravity filtration. And you have to do that sometimes because you can't always heat things up. Sometimes things respond poorly to heat. They decompose. So sometimes you have to come up with other separation techniques. So that's why we're teaching you the multiple things. Vacuum or suction filtration is very common, very popular. It's just faster than gravity filtration, and that is mostly why we do that. You're also going to be doing recrystallization. You're going to be given, you will be shown, someone being given a mixture of solids that have different solubilities, and then you heat them up, you cool them down, you collect the product. All right, and then you wouldn't actually be doing distillation, but you are going to be learning quite a bit about distillation. And then there's also a chromatography thing. And like I said, you're just going to be using that to determine purity by looking at by looking at retention factors. You can also determine purity. This is a neat thing with melting points. A mixture will always have a lower melting point than the pure solid because reasons. So you can determine the purity of something, to a rough degree by measuring the melting point of the thing. In that case, all you're doing is you're watching it to see when it melts. You measure the melting point at which it melts, and comparing that to the melting point of the pure substance. The closer they are, the purer it is. All right, so that is Lab 6, looking at different mixtures and different techniques. This is, in the hands-on lab, this is a long and difficult sort of thing in which you're working with a lot of unfamiliar techniques. So when we actually get to in-person lab stuff, you will be wanting, and hopefully you'll get a good amount of hands-on stuff here. As it is, they're going to be showing you a lot of different things, and they're going to be asking you questions about those different things. So I expect this to be a fairly long and complicated worksheet for you to work with. So be sure you give yourself plenty of time to get through this, to watch these videos probably multiple times. And I'm guessing each one of these is, only 5 minutes there, 5 minutes there, 5 minutes there. Well, they're doing a pretty good job of, 20 minutes. Okay, so they are 5 minutes, all right. So they're doing a pretty good job of keeping them reasonable, but nevertheless, they are going to be a significant investment of time in themselves as well. So this is going to take you several hours, I would think, to get through. So make sure you get through that. All right, and with that, I am done with this, and I will see you for lab stuff. Well, half of you in person, all of you online next week.